Hey, John here. Let's look at how we represent floating point numbers using the IEEE 754 representation scheme. All right. So these are notes coming from my RVLP manuscript. I'll put a link to it below this video or in my course website. All right. What are we going to do here? This is a very specific type of representation of floating point numbers. There's many other ways to do this. This is just one single way. All right. Turns out it's the way that most microprocessors use, especially any Macintosh PC, your cell phone, and all this stuff. This is an incredibly widely used standard today. Okay, quick review. Regular integer binary values that we've been talking about are represented using the powers of 2 to represent the place values of all the bits, right? So you end up with this 1, 2, 4, 8, 16, 32, 64, 128, and on for the powers of 2, representing the positions where if there's a 1 in each of these columns, you would accumulate this much magnitude to the number, the value that it represents if you're converting it to decimal, right? These are obviously decimal values representing the powers of 2. Just like decimal numbers, you got your ones, tens, hundreds, and thousands, you're representing the powers of 10. If you have a point in a decimal number, the value of the digits on the right are inverse powers of tens, right? So you would, in a decimal value, you would have tenths, hundredths, thousandths, and so on. In binary, just like these binary powers of 2, you'd have the binary powers of 2 going the other way. These are negative powers of 2, just like the negative powers of 10 would be in a decimal number, okay? This point here in a binary number is not called a decimal point because it's not a decimal number. It's a binary number. So this is a binary point, okay? Okay, and it kind of makes sense if you think about it. You know, you got your, if you start over on the left here and you move it to the right, what you see, they're all being divided by 2. 64 over divided by 2 is 32. Divided by 2 is 16. Divided by 2 is 8. Divided by 2 is 4. Divided by 2 is 2. Divided by 2 is 1. If you want to keep going, what makes sense? Well, half of 1 is a half. Half of that is a quarter, half of that is an eighth, and so on. So the powers to the left and the halves going, they're all powers of 2, all right? So again, think of it however you want, but you can certainly notice the continuation of a theme here in the right direction. All right, so the way we store these things in a machine in this format, we essentially use scientific notation, right? Now remember, in base 10, you used to see things like 2.7 times 10 to the negative 47th power. This would express a very small fractional value. There's the power here being negative. It means that you move the decimal place to the left 47 times. So that's a number very close to 0, okay? Now, in scientific notation, if you do this, you're not concerned with every single digit in the final value, all right? Because 10 to the negative 47 means there's 46 digits to the left of this 2. When I express it this way, they all have to be zeros. If I wanted to express them all, I'd have 42 digits that I would have to write in here, okay? The point here being that there is significant portion of the number is less than the total digits in there. It's not entirely accurate, okay? It's an approximate value, okay? That's a theme here with floating point numbers, whether they are in decimal or in binary. You know, it's only as accurate. It has what we call as much precision as you will see the Mantissa can represent. Okay, so this thingy over here to the left of the multiplication is formally called a mantissa, and then you have times whatever your number base is to the power of some exponent. In this case, the exponent was negative 47. All right. So if you were to do this in binary, it would be the mantissa times 2 to the exponential power. No problem. We have to normalize our numbers in this format. And by normalization, I mean, and we, again, probably forgot, but learned this in grade school, a normalized scientific notation number has a single digit here, a decimal point, followed by some number digits called, is for as many as the precision is that you're working with, however many significant figures you want to have in the ultimate value that you represent, and then you've got your times 10 to the whatever. In order to use this format, we need to have normalized binary numbers, which means you have to have some digit to the left of the binary point, followed by more digits to the right, and 2 to the power, okay? So to do that, let's look at C here. Here's an unnormalized binary number that represents negative 2.625, right? That would be negative 10, and in binary, 10 is 2, right? If it's this portion of it, an assigned magnitude, we call that, this unsigned value of this here with a negative in front of it, okay? And then you have a point in the 101 over here is a half plus 0 quarters plus 1/8. So that's the way this is 2 5/8. That's what this number here is, negative 2 5/8, all right? So that would be negative, however you're going to represent negative. We'll get into that in a minute. 2 point, whatever it comes out to 5/8. Okay, great. If you want to normalize that, you can have only one digit to the left of the binary point, just like in decimal, which means you now have to remember to multiply it by 2 to the first power so that you can remember to move the point back over here, all right, to get back to this number if you wanted to print it out in binary or whatever, okay? So 2.625 in decimal, converted to binary, normalized, looks like this, right? Because you got 1 point something, which is the significand, as I point out here, the thing to the right of the binary point. 1 point, the significand, times 2 to whatever power is needed to move the point. All right. Now, since all normalized binary numbers have to have a 1 here, there's no reason to store it, waste the memory to store it in every single time you store a value. So they just leave it off. So what we're going to find is we store the significand and we store this power. We know it's binary because by definition it's binary. We know it's normalized, so we know that this exists. So we have to remember, we have to represent the sign somehow. We need to store the significand and the power. Okay, so how do we do that? Well, this particular format divides up the memory of the machine like this. We have a 32-bit value. They have two different definitions. They have this 32-bit version. There's a table down here that shows you the 32 and the 64-bit version. This is called double precision floating point for this guy over here, and this is called single precision. So for lack of desire to want to put too many bits across the screen here, let's look at a single precision floating point number that represents this negative 2.625 value up here, right? So what do? We have a signed bit. Unlike 2's complement, the signed bit exists on its own in this format. If it's a 1, it's a negative number. If this is a 0, it's a positive number. This does not contribute to the magnitude of either the exponent or the significand in any way. All right? This is just 1 if it's negative. Okay? The exponent is stored here, and the significand is stored here. And you can see the significand. This one's obvious, right? You got the 0101 sitting here, right? Well, you know that it's got to be 0101 because that's what we had up here. So this thing goes right down here, as long as it's normalized, right? You have to have 1 point, and then whatever this is here, it just goes right in here, right? Now, obviously, it can only have so many significant figures. There's only 23 bits here, right? And in the double precision format, it can have only 52 bits. If you need more than that, it will round the value off. And we'll talk a little bit about that in a minute, okay? So what about this exponent? What the heck is this? That's supposed to be 2 to the first power. How the heck is that supposed to work? Well, this format is referred to what we call XS 127, right? And in double precision, the exponent is bigger, and it's XS 1023, right? So in single precision, it's XS 127, which means simply that you take the value in here and you subtract 127 from it. So here's, if you have this value here, we expand it like this, and we can work out and calculate, and you can see we're going to come up with the right answer, I hope. Okay, now what does this all come out to? All right, remember, always the significant would be prefixed with this 1 point something or other, right? So if you look at the values in here, there's your halves, your quarters, your eighths, and your sixteenths, right? So what do we got here? We got no halves, you got 1/4, no eighths, and you got 1/16, because remember, we normalized it. So you got your 1 point that comes from the boilerplate, which is this guy here, which we don't store in there. And then you add these guys up. Use your quarter and your 16th. So you just add them up. 1 plus your quarter plus your 16th. All right? Then you're going to multiply it by 2 to whatever this thing is in here, minus 127. All right? So what's 128 minus 127? That's 1. So now we've got our 2 to the 1th power here, right? That's this guy right there. And we have our normalized significant here in there, which comes out to mean this, 1 plus a quarter plus a 16th, okay? So just add them up and figure it all out. Well, we can use the distributive property of multiplication and multiply all this by 2. So you have 1 times 2 is 2, 2 quarters is a half, 2 sixteenths is an eighth, and you just add it up. 2 plus a half plus an eighth is 2 plus 0.5 plus 125 if you want to do it in decimals like this. And remember, we're still carrying around this negative sign the whole time. And we end up, you add them all up, and you get 2.625. All right, it's as simple as that. This weirdness with this exponent is I never really could figure this one out on my own. And of course, maybe if I read the actual spec, it would have told me. But when I was a kid, I never wanted to do my homework. And it wasn't until I actually met the guy that was the chair of the committee of IEEE 754. Truth story. I didn't know this, but I shared a hallway with the guy. My office and one of my jobs was in the same place this guy worked. And one day I was talking to somebody about calculating some values that we were having trouble with representing, and he heard us talking, and he happened to be walking by my office and leaned in. I mean, what are the odds of these things? This is insane. He leaned in, he says, could I help you with anything you might want to know about IEEE 754? And I said, you got to be kidding me. I happen to be the chair of the committee. I'm like, okay. The guy's name is Bill Cody. Google it, true story. When I used to work at Argonne National Laboratory. Anyway, he told me this right here. And he told me the reason that they use this weird format right here, what I considered weird until then, was that if you look at the magnitude of all the values in floating point representation, if you store them like this, and you just ignore that they're floating point numbers, and you pretend that all these bits represent a 2's complement signed binary integer, then you can compare their magnitude. You can tell which one's larger by just simply treating them as signed binary numbers, which is brilliant, quite frankly. It doesn't matter, in a way, it doesn't matter how you order this and whether you use XS 127 or not, but by choosing this, they eliminated the need for people that manufacture microprocessors to have extra circuitry and transistors and stuff in the CPU to compare the magnitude of two numbers. If you say if X is greater than Y, and those two variables are floating point numbers, you don't have to worry about it. Just compare them as if they're integers and then go on your merry way. Absolutely wonderful. Anyway, this is what this paragraph here talks a little bit about, an observation that was made. So when you get frustrated as to why they chose this, be thankful, because he saves you money and energy and you know, real estate on the silicon. Once again, removing transistors saves power and money and everything else. So it turns out to be a great idea. It just is not so obvious from this side looking backwards at it, okay? All right, so this also presents a couple of problems, right? If every value that's ever stored in here has this implied value of 1 that's not stored in the significand, then there's no way to represent the value 0. when you encode it like this. Now, that's a bit of a problem. So what they decided was, I say, everything else works beautifully, and in order to maintain the ability to compare the magnitude of two of these numbers as if they were integers, they make a special case for the value of 0. So the representation of 0 is simply an exponent that's all zeros and a significand that's all zeros. All right, now we come back up here. What does that mean? That just means there has to be all zeros along in here. If there are all zeros, it's a 0. If the sign bit is a 0, then then the entire value is 0. All the bits are zeros, okay? And that represents 0. Now, because they formally defined it as simply meaning these bits all being 0, the magnitude being 0, they have two different ways to represent it. They have a positive 0 and they have a negative 0. Now, that actually comes in handy for certain kinds of math. As you converge closer and closer to 0 from the negative side, that it could become 0 due to rounding. You might actually want to represent negative 0, suggesting that, it's become 0 from the negative side, but doesn't really equal 0 quite yet. And that can be useful in certain kinds of math, all right? So down here I mentioned the definition then therefore allows for positive negative 0, okay? In order for the integer comparison logic to still work, we also need to deal with the idea of what happens if things get too big. So here we talk about infinities, right? Well, what happens if the exponent is all ones, the mantissa is all zeros, and the sign is 0? Well, that is a relatively large positive number in binary. That means all these are ones here, and the rest of this is all zeros, okay? Now, the reason I would have expected them to have all these be set to ones as well. I don't know why they didn't do that. I should have asked Bill that while we were talking, but nonetheless, this is how this thing works. So if you have a 1 here and all ones in the exponent here and all zeros in the mantissa, that would be negative infinity there, okay? Now, I guess one of the reasons that they keep these things formally specified in that case is because if there are other values, is my point. How do you represent things like 0 to the 0th power? Right? That's not something that converges on 0, nor is it something that converges on infinity. How do you represent those things? You represent them using a special bit pattern in the mantissa in here, or the significand, I should say, that represents not a number. And they have a couple of different kinds of not a number that they encode as well. So, you, of course, can go ahead and read the specification for all those extra fancy things that they can also represent. My point is that these infinity definitions and 0 and so on, they leave a lot of possible bit patterns that are unused in this format, and it turns out that many of them are reserved for other purposes of special case values, all right? You have this notion of underflow areas and overflow areas, and by that it simply means as the numbers get too big, as the exponent gets bigger and bigger and bigger, if this exponent becomes all ones, as it gets gigantic, it gets closer and closer to the representation of positive infinity, all right? So once you've hit a value where you got the maximum exponent, you can just set all this stuff to 0 and just say, I've gotten so large I can't represent it anymore, so I'm going to just converge on infinity, all right? Now, that's a type of overflow for floating point numbers, and they handle it very differently, as you now notice, than we do when we have integer numbers. In floating point numbers, this, I guess, is similar to what you'd call saturation arithmetic. As the number gets bigger and bigger and bigger, it doesn't wrap around. It just stays at the biggest possible value, which by definition in floating point numbers is simply infinity. Now, that happens as they get too big, right? If you end up converging towards 0, in other words, as this exponent gets smaller and smaller and smaller, it'll eventually go all the way down to 0 and then minus 127, so it'll be 2 to the negative 127th power. That's a very small value, all right? Once this exponent becomes all zeros, we say you have become, it has underflowed, it has converged upon 0, And that is what we call an underflow operation. And this is kind of why, as I said earlier, they have a positive 0 and a negative 0, so that they can simply, if you have negative followed by all zeros over here, you're just saying that I have underflowed towards 0 from the negative side. All right? That's why they did that. And the final observation is the case with all scientific notation. As the number gets closer to 0, the resolution is very small, right? The distance between numbers that are expressed in 2 to the negative 127th power, those are teeny, teeny, tiny numbers. And as the significand changes its value, you're making incredibly small steps across the number line, right? But as the significand gets bigger, like 2 to the 128th power, well, here's 23 of the 128 total bits way off to the right here, off the screen even, that represents the total number of bits in that value. Right? Well, if I add 1 to this guy right here, I'm adding 1 followed by all those other zeros, the other 100 or so zeros over here. I'm making massive leaps, huge strides in magnitude as I make these steps. So that's the point of this last bullet down here. So the numbers have higher resolution on the number line when the exponent is small, all right? And obviously a low resolution, large leaps between them as the exponent gets larger, and that's true in scientific notation as well. And I got a little note to myself, someday draw a nice little picture in here. Okay, maybe I'll do that over Christmas. I don't know. Anyway, accuracy. Okay, so this is the main takeaway of this dialogue. Let's now look at some issues that kind of come into play. If, like I said, this whole accuracy, what happens when the exponent starts getting really big and you start adding zeros over here, or what happens when it starts getting really small? What you're really doing is adding zeros on the left. So you have a binary point 0, 0, 0, 0, 0 followed by a bunch of bits, right? So you end up with the ability to have either accurate numbers near 0 or very coarse numbers that are far away from 0 in either positive or negative direction. So I put together this little program. I don't know if you know what a union is, right? So let's look at this really quick. This simply means to tell the CPU that this variable I and the variable f here are to be stored in the exact same memory location. So if I set this value f to some number, and then I use this variable I, what I'm using are the bits that are represented by this floating point value. And I do this so I can print out these values in hex, right? So what I did is I created an X and a Y using this float bin union that we just looked at here. And then what I'm going to do is print it out. See how I say x.f and x.i and so on? Look what's going on here. In C, this is how you print out a floating point number that's given by this parameter over here. This is how I print out an 8-digit hexadecimal value as given by this parameter over here. To print out a hexadecimal value, I need to give it an integer variable in C. To print out a floating point number, I need to give it a floating point variable. So these two things, x.f and x.i, are literally the same bits in the machine memory. However, they're interpreted differently. The x.f is interpreted as if it is a floating point number, and it will be printed out as such, like this. The x.i is this version of the exact same bits in memory that'll be treated like an unsigned integer and printed out in hexadecimal form like this. All right? So I print out this x variable in 2 different ways, and I print out a y variable in 2 different ways over here. All right? So what happens here? I say x.f equals 1.0. While it's greater than 1 divided by 1024, 1/1000th, roughly speaking, in decimal, I say the y version equals negative x, okay? And then I print them both out, and then what do? I divide the x variable by 2, the floating point value, by 2. All right, and then I just go around in this loop. So let's see what's going on here. I start out with 1.0 because I set it to 1.0 here. And every time through the loop, it's half as much as it was before. And look what's happening over here. The hex value, this is showing us what the bits are in memory that represent this value over here. So 1.0 in IEEE-754 floating point number is 3F800000. And a negative version of the same value is BF8000000. What's the difference between B and 3? In binary, the 3 is a 0011. A B is a 1011. So the only difference between this value here and this value over there is that the most significant bit in this one is a 0, and the most significant bit in this one over here is a 1. Exactly as shown in the diagram right up here. Okay? So let's look at some of these other numbers. If I keep dividing it by 2, eventually it'll converge on 0. Okay? It eventually will not be able to represent any values anymore. If I did it forever, I mean, it would burn up a lot of paper here. But you can start to see this thing getting a little bit out of whack as it goes. The value, half, quarter, eighth, this is a 16th. That's a 32nd, a 64th. Oh, you know, what is that, 128th, a 256th, a 512th, and so on. And you can sort of see what's going on here. This value here, the bits that represent the exponent are becoming less and less and less as it goes down. And again, remember, I can use the game due to the encoding that if I look at these two as signed binary values, this one here is larger than this one here, and that's larger than this one here, and so on. Okay, so you can see this all in action and working. Same thing is true on the negative side. If you convert this, I should have probably printed out the integer numeric value of this. It'd be some massively huge negative value, as well, this will be a massively huge positive value. If you printed this hex value out as an unsigned integer, or rather a signed integer in these two cases, right? And you'd see them going up and down in both cases. But it's just as easy to see the size getting larger and smaller in hex as well. All right? Okay. So this gives you an example of some clean encodings, right? Because you know these are what I would call clean because it's a half, a quarter, an eighth, a 16th, and so on. And in the significant, there's actually no bits are set in the significant at all. The only thing we're dealing with is the exponent, right? Because the mantissa is 1 point and then followed by the significant. And since there's only one binary point, one digit, binary digit needs to be set for each one of these values, you can see clearly in here that all the bits representing the significant are always zeros, all right? This thing going back and forth between 8 and 0 and so on is the exponent, because if you look at the bit positions on these guys, it goes down to 23. And the hexadecimal digits are in 4s, right? So here's the most significant hex digit. Here's the next significant hex digit. And this bit here is part of the hex digit that represents these 4 bits right there. So with the significant always set to 0, if I play around with the exponent, sometimes this hex digit here would be an 8, and sometimes it would be a 0. I mean, if you really think about it, and that's what's going on in here as we keep dividing them by 2. All right. Now let's see what happens. Just like in decimal, we have what's going on here. Okay. Just like in decimal scientific notations, if they get too big, we start losing this precision, right? So down here, you can sort of see what's going on. If I keep multiplying, I wrote this loop here. Instead of setting it to 1 and dividing it by 2, I set it to 10 in decimal, and I keep multiplying it by 10. And again, I print it out the same way. So let's look and see what's happening here. If I set it to 10, there's the encoding in hex, right? If I keep multiplying it by 10 in decimal, this thing is bigger and bigger and bigger, and all of a sudden, oh, it's starting to get rounded off. I mean, that's not too bad, right? Because this should be 1 with however many, I think this is 10 zeros, right? 1 0, 2 zeros, 3 zeros, 4, 5, 6, 7, 8, 9. This is 10 zeros. So that's 1 times 10 to the 10th power. And once you go to 11 zeros in decimal, there's not enough bits in binary to represent that with the 127, or whether the, where's my little picture up here with the 23 bits, right? 0 through 22. These 23 bits can only represent decimal values up to a certain size before we start having to round them off, right? Remember, I can say when we're near 0, we can take all kinds of small steps and be very accurate. But as the number gets really big, we can't take small steps anymore. We have to take increasingly larger steps. And if there doesn't happen to be a step on a value you want, it'll have to round it to the nearest thing it's got. So rather than having 1 with 11 zeros, it comes very close with 99999999999 and 7952. You add a few to this thing, and you end up with 1 with 11 zeros, right? You'll have to add, what about 2001, I don't know, 2048 to it or something like that in order to round this thing up to where it belongs. And as you can see in the hex values over here, you can, in your mind, you can see the binary bits becoming further and further to the right in the significand. And by here, we've run out of precision. All right. Now, it turns out that these things rounded off okay anyway, but eventually you get to the point where you can't represent it anymore. How many significant figures do you have? Well, in binary, you don't have enough to represent these decimal values exactly the way this program tried to calculate them, right? And I'm multiplying it by 10 around and around in this loop, so if it ever gets out of whack, it will continue to amplify that mistake. Right? So this logic has two problems. One, it shows that after a certain while, you cannot accurately represent values. It also shows an accumulation of error. All right. Now, it's not super obvious in this example, but it is if you go the other way. Let's look at values that are less than 1 and sort of see what's going on. Now, we're not going to converge on 0. All we're going to do is count. We're going to count up by tenths. Now, in decimal, we all know that 1/3 cannot be represented accurately, right? In decimal, it's 0.33333, and it's a repeating, non-terminating decimal, we say, right? Well, it just so happens that in binary, 0.1, as in 1/10, is a non-repeating, or rather, it's a non-terminating, it's a repeating, non-terminating binary value. Okay, and we'll see that in a second. So what happens is I set my x variable to a value that cannot be accurately represented, and then I go into this loop and I continuously add a value that cannot be accurately represented to it. So what we're going to see here is a continuously increasing error fuzz of rounding that goes on and on and on and on, okay? And it's very unfortunate that this is that 1/10 happens to be one of the values that is commonly occurring in our lives that cannot be accurately represented in binary floating point numbers. And by that, I'm referring to financial systems, okay? If you don't write your software correctly, you are doing a lot of rounding if you have anything that comes out in dimes, is what I'm saying, all right? Or tenths of dollars or whatever currency you have. Okay, so let's see what happens here. So the very first time through the loop, I set it to equal to 0.1 and I print it out. Well, it can't even print out the floating point value accurately because it can't be repeated, because it can't be presented accurately, right? So here's this repeating non-terminating value here, CCCCCC. And there's no way to tell the computer, oh, by the way, that's repeating and non-terminating. So it gets to the last digit over here, and it wants to keep putting C's over here, but it can't. So what is it going to do? It's got to round the last one. Well, should I round it up or down? Well, rounding it up is better than down in this case because the next digit would have been a C over here. And that's closer to up than down, right? The midpoint is 8 in hex. It's like rounding up when you get to 5 in decimal, right? So this guy rounds it up, and you end up with this value here. A little teeny bit of an error over here. Now we add it, no, we double the error, okay? Okay. Keep on adding your tenth, the error gets bigger and bigger, and the rounding is going nuts. Eventually, we're lucky, it rounds itself back to where it's supposed to be, because you got a tenth, a 0.2, 0.3, 0.4, and 0.5. It better be 0.5. And you can see it cleanly represents 0.5. If you work this all out using the IEEE table above, you can figure out that is an accurate 0.5. However, as we keep adding this tenth that's inaccurate. By the time we get here, we've now irreversibly lost our ability to maintain any accuracy. Because at this point, we're rounding in the other direction. These all round up ever so slightly, and then you got all these threes, and you've already rounded up too far here that he can't round it back down enough when he gets down to here. So the error, look at how big the error is getting on here. And then we get to the 0.8, we get to 0.9, and it cannot figure out how to round itself back down to 1.0, which is really a bummer, because clearly 1.0 is an even power of 2, and it should be perfectly represented, and it's ever so close. It's off by one least significant bit in the significant, all right? And it's off by that much already over here. And once you've gotten this far, you can never get back. So you get 1.1, 1.2, your 1.5 should be accurately represented, but you're off by this much already. It's crazy. And you never even get to 2. You step right over it, right? So you're at 1.9 and change, and then you get to 2 and change, and this loop says, well, less than 2, so therefore it never really equals 2, therefore it's never going to print out however close it got to 2, all right? It just bails out. Now, this will get worse and worse and worse as it goes. That can be an enormous problem if you're doing a lot of math and floating point numbers in a loop and you're accumulating something. You have to be very careful how you write that code. If I wanted to count by tenths and I did not want to accumulate errors, here's one way I could do it. So instead of what I did up there, I could have set an integer variable, I. Here is an int. What if I just set I to 1? And every time through my loop, I add 1, an integer 1 to a 1. And then it is exactly 2. Then it is exactly 3, and so on. There's no rounding here. This will always be exact values. And then in my loop, I just simply recalculate however many tenths. Okay, now 1 divided by 10 is still going to give me the same crummy error. Okay, however, I will not accumulate it using this logic. Let's see what happens here. We get up to our half the same way we did before. These are all the same values we had above. You can go back and scroll back and see that that's true. The 0.6, we got the same value here. But now, when we get to our 0.7 value, instead of rounding up, we rounded down. This value here is a lot closer to 0.7. What are we off by? 119 from 0.7? Well, what were we up here? We were off by 477, whatever, point is something 477, and this one down here is only off by same number of digits, and only 119. All right, so this is far more accurate than the previous one. When we get to 0.8, we're only off by 119. When we get to 0.9, we're off by, I don't know, about 200 and whatever. It comes at 28 or something like that. And by the time we get to 1.0, we're exact. Well, the other one was not exact at 1.0. It had accumulated enough error by the time it got to here, it could never get to 1.0. The previous one never got to 1.5 accurately either. Previous one never got to 2.0 accurate either. So this is a much more accurate way of dealing with maintaining a continuously accumulating, or in this case, simply counting in a loop that deals with this rounding problem in such a way that the rounding becomes increasingly accurate when it can be, and only becomes as inaccurate as it must be as it goes, and doesn't continuously get worse and worse and worse and worse and worse. And I show, of course, both the positive and negative values of each of these things. I suggest you look through here and confirm that what I just told you is actually true if you're ever going to write any real amount of floating point math, especially if you're dealing with financial investments and coefficients of equations that are dealing with large numbers and continuously accumulate. Because if you have a large coefficient and you're rounding, oh my gosh, all of a sudden now these values could be significantly out of whack. And the last thing you want to do is screw up your investment portfolio because you foolishly did not realize how floating point numbers were really represented inside the computer. All right, so that's a nice introduction, I think, to floating point numbers and how they're represented in IEEE 754 format. So thanks for watching. Bye.